have control of the lights in the back? Anybody hit that switch?
So, just the front one. You good?
Oh no.
Okay, never mind. Have a seat. It is what it is. This never really comes in all that great on the video, so more encouragement to show up. Don't be surprised also if I start posting videos a day or so late. That can happen periodically. So I think we're out of the period where we have to rely on this stuff. Again, it's meant for you to do. We were looking at this last time, and there's a lot going on in this picture. So what we had done is we had flipped a coin 10 times to try to estimate what the probability of the coin was. So there's this probability P for a coin. We're all familiar with the concept. There's also the probability of you knowing that probability. So we're placing a probability distribution on a probability. And if that seems weird to you, it's not. So it's exactly the same as placing a probability distribution on any parameter. So probabilities over probabilities make sense to me if I'm trying to estimate the uncertainty of a probability. And so the probability of the probability is the expression of uncertainty of that parameter. And this is what distinguishes a Bayesian. So this is the key feature. That a Bayesian conditions on everything they know, the data, and they place probability measures on things that they don't know. This example is relatively simple. We can work it out in closed form, and it's one-dimensional. So there's only one parameter of interest that we're trying to estimate. So everything that I'm going to show you is going to lend itself to high-dimensional examples, but later on we'll need to use some computational facilities to do our estimation. So, but I kind of like this example because it illustrates a lot of different things to us. So let me just remind us what the problem is. So our problem is xi's are coming from a Bernoulli with parameter p. And that parameter lives between 0 and 1. You could make it include 0 and 1 if you wanted to. So I wouldn't consider that something like a random process because there's no variability, but it is. So it's just a point mass on something. So if p was 1, we'd always see 1s. If p was 0, we'd always see 0s. That is still a random measure. So point masses have that. So usually the only interesting problem we would ever have to solve is the one where we're not including 1s or 0s. Otherwise, why are we asking the question? I'll also say that different p's, the inferences you do sometimes can induce different properties. So if you're a frequentist or something like that, I'm not saying that there's anything wrong with it. If you're an asymptotic frequentist, I should say, and you're going to leverage the central limit theorem to estimate p, depending on what p is, you'll get different performance out of your inferences. So p close to the middle, we can usually estimate that p relatively quickly. So because there's a lot of variability. So we see lots of 1s and 0s. If I wanted a precise estimate up to the same amount of decimal points, and p was 0.0001, it'd be very hard to estimate that p. So we'd see a ton of 0s. Periodically, we'd see a 1. We wouldn't know anything until we finally saw that 1. So it's a rare event. And so in models with rare events, the performance is usually a little bit tricky. There's a boundary effect as well, hard boundary on what p can be. And so a lot of times frequentist methods suffer when you're close to the boundaries. And we'll illustrate that throughout this class. So I'm going to just try to show you procedurally how a Bayesian operates. And we'll talk about some key features to this analysis as well. We'll see this sort of thing for a few different distributions. So I like to start with the binomial distribution. I said Bernoulli here. You'll realize soon it doesn't matter how I voice this problem. The book likes to start with a normal example. We're all familiar with normal distributions. The trouble is with the normal is the data lives in a continuum between negative infinity and infinity, and the distribution looks like that bell-shaped curve we're all used to seeing. The likelihood looks entirely similar to that. And so it's a continuum, it just shifts the distribution. And the likelihood is not a distribution, which might confuse some of us. but the sampling frequency distribution, that is a distribution, even though they look the same. This example, the data is coming at us in a very non-continuous way. It's coin flips. And the likelihood is a continuous thing. So it'll help to differentiate these concepts to you a little bit better. Okay, so I'm just going to point to some things real quickly. My legend's pretty bad here. I doubt you can see it. Let me see if I can make that bigger. So red is the likelihood. I'll just write this down. Red is the likelihood. Dotted red, so dash red, is the posterior. And the black, dotted, dash black, is the prior. These are all the pieces of a Bayesian analysis that a Bayesian likes to think about. The one I like to think about the most, more than anything, is the posterior distribution. So, of course, I think about the prior in what I'm doing to induce the posterior, but my inferences are going to come from the posterior. That's the thing I want to talk about. I want to talk about its properties. I want to talk about the point estimators that come out of it. I want to talk about how it describes uncertainty. But ultimately, this curve integrates to 1 underneath the curve. And so, if I think about the posterior distribution, the dashed line, is it the dash? Yes. I think. I can't. Let's rerun it. That's exactly the picture that I was looking at when we left class last time. So I'll just rerun everything. Same numbers. There's a truth out there. To flip the coin, I need a coin. So its probability is 0.7. And the only place I use that is to show you where the truth is. So my hyperparameters in the prior, I set them to be 1/2 and 1/2. We can look at other values in a bit. And I flip the coin 10 times. So that's what the arguments are. All this code is available to you. Okay, so blue is the truth. Black dashed is the prior. We've got that right. And red dashed is the likelihood. I got this wrong. After, what you'll notice is after a while I can't distinguish them very well. At the very beginning, they look very different from each other. And so I will say the likelihood is probably the driving force of all Bayesian analyses. So the prior helps regularize the space and make it so weird things don't happen, aka the boundaries are funny. They behave funny, and so this prior right here is placing extra mass around the boundaries. I'll talk about that later, what that does and where this prior came from. But right now we can think of it as an arbitrary choice. Saying that is a very good choice. And you'll be probably using this choice if you're a Bayesian later on. There's other good choices as well, for different reasons. Okay, so in one coin flip, we've noticed that the likelihood is just this straight line right here. Once I multiply that straight line, and what I mean is just point-wise, if I take this value, I multiply it by the prior, I get that thing. I've normalized everything as well. So you might be wondering why things are going up and down relative to each other. I've normalized everything so that it all adds up to 1 underneath. So you can see where I'm placing mass. Likelihoods, that doesn't have any real reason. What we said before is likelihoods are proportional. They're the same likelihood function proportional to any positive constant. Bayesians like to put it on some sort of a relative scale so that everything adds to 1, but they have to multiply by a prior before doing that. Okay, so I want to talk about all these different pieces. Let's just flip the coin a couple more times and see what we're in store for. That posterior is going to move around. We'll automate that. Let me show you what the likelihood looks like. So first, the sampling distribution. So the sampling distribution look like this. Px, my notation is cap x is just my collection of coin flips. These are ones and zeros. So element of 0 or 1. I goes from 1 to n. So some bounds on the problem. So I'm going to have those n coin flips. This is conditional on some probability p. And this thing is going to look like this. Product, I goes from 1 to n, p to the xi, 1 minus p to the 1 minus xi, which is the same as p to the sum of the xi's times 1 minus p to the n minus sum of the xi's. So that's our joint sampling distribution. This accounts, it's not the same as a binomial distribution because this is a distribution on a vector quantity. So ones and zeros. I'll show you that's how those ones and zeros came about. The binomial sampling distribution is similar. So the binomial looks like this. It accounts for n and p, and it looks like px, where x, in our case, our data, is going to be the sum of the xi's. So I've done the first thing that statisticians do all the time. I've used this variable differently, x. So this is my sum of the xi's. That's my random variable. In this notation, my x is the collection of ones and zeros. They have the same information about p. So both of those things. So given p is equal to n, choose sum of the xi's, times p, sum of the xi's, 1 minus p, n minus sum of the xi's. The key point to me is that these have the same kernels. So this function right here, all the stuff that depends on p, shows up right there. This is just a positive constant. And so as a function of p, they're the same functions. They're the same likelihood functions. And that's a good way to tell they have the same information about p. So if the likelihood curve is the same curve, it has the same info about p. If you're a fundamental ardent likelihoodist, you believe that very critically. So, and anybody that tells you otherwise, you get into a huge fight over it. So, we'll refrain. So, there's good reason to think these two functions have the same information. So if I compare in a ratio sense different p's to each other, I'm going to be coming up with the same ratios. The normalizing constants will cancel out of the ratio. They don't change with p. Okay, so this is what our likelihood looks like. Or it looks like this right here. If you want to multiply by any other positive number, they're the same likelihood functions. So for our first coin flip, we saw 1. And so we ended up having our likelihood for coin flip 1 So I'll say 1. We ended up seeing a 1. So x1 was equal to a 1. And so we had p to the 1 times 1 minus p to the 1 minus 1, which is p, which is just that straight line that we saw. And if we had seen a 0, our likelihood function would be 1 minus p. And it would be a line going the other direction. So that's what the likelihood looks like. A Bayesian is interested in more than just the likelihood. The likelihood is probably the inspiration for all of this stuff. But people used to quibble about the likelihood, whether or not you should use likelihoods and what is it. We had a rough conversation about this on Friday, where we were discussing the difference between a random variable and just a variable. So a likelihood function is not a probability statement. It's a relative statement about the various heights So in a ratio sense, how we compare different likelihood values to each other. So for instance, if I had likelihood, if my likelihood looked like this value right here was 3, I'll say, let's call this P tilde, call this P double tilde. Let's say this value right here is a 1, and that value right there is a 3, then the relative likelihood comparing these two things would say this is 3 times more likely than that. So P tilde over P double tilde is equal to 3. So it says that value is 3 times more likely than that. So what do I think when I see that? I think both could happen, especially if I saw this multimodal thing. So I think there's a lot of information in likelihood functions that's not just their maximum likelihood value. So some people will just use the likelihood maximum value, and a Bayesian is going to use that whole curve. Okay, so likelihoods aren't the only thing going. If we want a posterior distribution, we need a prior distribution as well. So let's talk about priors. So to get our posterior, so we're going to have P to the P given X. So you might not like that I've got P, which is a function of a parameter P. You'll see people do that all the time. So you have to be really careful about what's an operator, what's a parameter. Let's be a little bit more polite right here. I'm going to say pi. So that's my posterior distribution. This is going to be equal to my likelihood function times my prior distribution. And so I'm just going to call this pi prior. And it's on the parameter P. Let's call this pi post for posterior. I wrote down equal, so we need to normalize this. Likelihood P times our prior. dp. This is always a definite integral on the bottom. The p's are gone. There's no more variable p. So this is one of the most critical mistakes that people make in my class, is I'll work through this integral, and it will still have a p remaining in it. And it tells me two things. Your calculus has an error, but you don't understand what you just did. So all of the action is up here. So the function of p is all right there. And I could substitute my equation. I could grab my likelihood function and go grab my sampling distribution, whether it be this one or this one, and I can substitute that in. It's no longer the sampling distribution, it's the likelihood function, because the data is fixed and plugged into it, and it's a function over p. And regardless of which one I plugged in, if I pick this one, I would have that normalizing constant in the top and the bottom, and it would cancel. So let's just do this. So this thing is going to be equal to, I'll do this if you'd like, sum of the xi's, so you can see them cancel each other. P to the sum of the xi's, 1 minus p to the n minus sum of the xi's. Divided by, oops, I need a prior, times my prior. Integrate over the exact same thing. So this is just our normalizing constant. Sum of the xi's, 1 minus p, n minus sum of the xi's. Put some i's in there. dp 0 to 1. So here's the magic move. This happens for when you're deriving the posterior distribution. This is always going to happen. When we do decision theory and hypothesis testing, we're going to have to be way more careful about this stuff. There are some surprises in store, but not for a couple months. So those things cancel each other. That doesn't have anything to do with P, so I can pull it out from the integrand, cancel, and that would happen regardless. Just as long as the likelihoods are proportional, you can multiply by any constant you want. My favorite constant to multiply by when everything is arbitrary is, there's only one number I can't use, but we need it to be positive. It's always 1. So a lot of times I'm just thinking about the number 1 and pre-multiplying it by it. Okay, we need to talk about this, the prior distribution. So let me give you a definition. If pi post, so I'm going to just make this general right here, theta, so this is just an arbitrary parameter. In our example, theta is equal to p. So a lot of times when I say theta, I mean the things we don't know. The things that I'm putting the probability measure on. So I like to use this variable, and almost everybody uses theta. So I just want to make this definition a little bit more general. So given x, the key point is that this is representing the posterior distribution on some parameters theta. So in a Bernoulli distribution, that parameter would be p. If we're dealing with a normal distribution, there's 2 parameters there. I usually talk about a mu and a sigma. We'll go into 2-dimensional analyses soon. So it's just your parameters. So if pi post is an element, I'm going to say f, this is going to denote some family of distributions. So examples, e.g. normal, Poisson, binomial, gamma. I guess I've grabbed everything from the exponential family. So Weibel, non-exponential family distribution. You might not know what all these are. Etc. And pi prior on theta is also a member of f. And so if the posterior is normal and the prior is normal, then we'll say that the prior is conjugate. So that's the language that's used. And Raffia came up with this language. I find it to be confusing because people use the word conjugate different in different fields. So if you've taken a complex analysis class, it has nothing to do with that. So unfortunately, it's one of these recycled words you'll hear in mathematics that they are loosely related to each other. But if this is an element of f, and that's an element of f, if they both belong to the same distributional family, then pi prior on theta is conjugate. That's a definition. Now there's all kinds of reasons that we want to consider conjugate priors. And we're going to get more reasons as we go through this class. But right now, it's convenient. And that's not a good reason. So it will turn into a really good reason that it's convenient, and it also has a lot of other properties as well. Sometimes they're not the right priors to use, and that's really what this class is all about, learning the different properties. But right now it's easy because if I know how to talk about my prior and I know all my properties of my prior, then I instantaneously know how to analyze my posterior distribution. A lot of times, these are tractable solutions. I can write them down on a chalkboard. So there's priors we could come up with. They have other properties that I could never write down. You can still use them because we have computers, but being able to write it down and look at it, it's nice for us. I used to think it doesn't matter at all whether or not we're able to look at something. It's definitely helpful. So we can analyze asymptotic properties, we can do math, we can think about it. Okay, so let's just write down our problem. So back to our Bernoulli binomial problem. So we have this. Pi post given x is going to be proportional to, and I'm going to start using this symbol, but it means that I define the equation up to its kernel, and you can multiply this by any positive constant and it's still the same function. So that's what this symbol means. Proportional. Again, likelihoods can only be expressed up to proportionality. So what I'm going to do, very commonly, there are some problems where I can't get away with this and I have to keep track of the normalizing constant. But in most of the problems I'm going to do in the early part of class, I'm just going to be throwing it away. So, and I'll recover it at the end because I'll know the properties of my posterior because I know all the properties of my prior. So this is going to be P times sum of the xi's, 1 minus P n minus sum of the xi's, times pi prior. Now, periodically, I'll read through Stack Exchange and I see this same question all the time. How do I recognize, what's the magic trick for recognizing what the conjugate prior is? And the difficult thing is, you just need to know a lot of distributions and understand how algebra works. So it's kind of up to your imagination. So I know a bunch of distributions, and I could probably recognize what is conjugate, but what I'm really doing in my head is I'm just kind of trial and erroring this thing. So if I had something with like e to the minus blah, 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 blah over here, the question would be if I multiplied by that, would I still have that same form over here? And the answer is no. So if I made this a uniform distribution, would this always be uniform? And the answer is no, because I'd take something that's uniform between 0 and 1, and I would get something that's non-uniform over here. We'll talk about the uniform distribution in a moment, because some people might be inclined to think uniform would be really good prior. Feel comfortable about that. And if I could add one thing in the universe, is to be able to tell you that's okay all the time, but it can really mess up your analyses. We'll be talking about this. How bad would it be in this case? Probably not horrible, but near the boundaries, I would be able to outperform you if P was small or P is big. You'll be able to convince yourself of this after homework number 1. So right now, only homework 0 is out, so it's coming. So the question is what is the conjugate prior? And I know half of you know. It should be bigger, because I've already told you. I'll just point out, you can't know without staring at this, the likelihood. You have to be staring at this and thinking, how do I slide this through, multiplying it through, so that I get a function of the exact same form? And again, there's not a magic wand for doing this. You just need to know lots of different distributions. But the first thing that jumps out at me is that distribution, or not distribution, that likelihood function, if I thought about it as a distribution, looks awfully familiar to me. So, and those of you who don't know, that looks like the kernel of a beta. So let me just tell you about a beta distribution. Sorry to take away the thunder from a lot of you guys. I just know a bunch of you do know how to do this. And some of you, this is the first time you've ever seen this. Okay, let me just ask. Who doesn't know what a beta distribution is? Just one? 3? Okay. A bashful 4? So, okay, well, let me just show you what it is real quickly. So, beta. This is the beta density function. Sometimes I will speak incorrectly and I'll say this is the beta distribution, but the distribution is the measure. It's the thing that lives between 0 and 1. Where the density functions can go above 1. They're just positive. Okay, so if you want to take a density like a normal distribution, collapse its variance really small, and it'll get as peaky as you want. So how high will it go? Eventually, when you make it 0, it'll go infinitely high. So it's a concept you can grapple with. Okay, a beta density looks like this. P to the alpha minus 1, 1 minus P to the beta minus 1. And there's some restrictions on here. So of course, P is going to measure the same thing we had before, lives between 0 and 1. And alpha and beta, they're both positive parameters. You can use the zeros in here, and some people will. That's called Haldane's prior. It's talked about in your book. But usually people make these things positive, so that it's an actual probability distribution, so that it integrates. So if you look at Wikipedia, they'll tell you, these are the bounds of support for everything. And so I'm just going to call this pi p right here, because that's my distribution. And I haven't said this is my prior yet, but this will be my prior. And I said this thing is equal, so it ends up having this other thing right here that normalizes everything. So this is the normalizing constant. And I'll try to make it a little bit bigger. I'll call it cap beta, because there's a beta sitting there. So this is my normalizing constant. But the key point, all the shape is in this part, right here. It looks a heck of a lot like that. You can probably already convince yourself if you multiply through, it's still the same form of a function. So let me just tell you what this coefficient is. So this thing, no surprise, is just going to be equal to the integral of p to the alpha minus 1 minus p dt. So the way you normalize things, you add everything up upstairs and you divide by it. It means when you add everything across everything, it's going to be bounded by 1. So that's called a beta function. And later on, we'll see a connection between that function and a gamma function, if you're familiar with it, and there's a relationship to factorials. So this looks like gamma alpha plus beta, or gamma alpha gamma beta. Some of you might know that. I never use it for anything. So it's never been useful in my life to know that.
So this is beta minus 1.
Yeah, this one's inverted right here. So I need to divide by this thing right here. It's a good notational question. So I could have just divided by that function down there. So that's why it's the normalizer. Add everything up downstairs, see how it adds, divide by that same thing. So long as I didn't put any negative junk in here, it will normalize to 1. You can never have negative junk in there. So that's another critical error I see when people give me densities that are negative. So, okay, so lots of betas floating around. So this is a beta density. It has parameters, alpha and beta, and the normalizing constant is a beta function. So don't be confused by all the different uses of the word beta there. This is as bad as it gets. So I don't think we have it that bad for any other distribution. But that's what a beta looks like, and the question is what does this curve look like? But we've been seeing it evolve and fluctuate. So if I ended up using this right here. And I ended up taking my likelihood, P sum of the xi's, 1 minus P, n minus sum of the xi's. And I multiplied by this prior. Now keep in mind, I've gotten rid of the normalizing constant right here. I've gotten rid of it. It doesn't matter. I'm not going to write it down. I could write down any positive number there. It'd still be the likelihood. But since I'm chucking my normalizing constants and I'm just describing everything up to proportionality, once I do that once, you might as well throw everything away. So there's no point in bookkeeping all of it. So the normalizing constant here is this, right here. So I've said repeatedly, I don't use that thing. So I usually just toss it. So it does mean something to me. It's the normalizing constant. And of course, when I compute everything, I am using that, but I'm not using it explicitly. So I never actually code that thing up. So I can get rid of that normalizing constant as well. So P to the alpha minus 1, 1 minus P to the beta minus 1. And I'll just remind you there was a normalizing constant here, and I got rid of both of them. And so my posterior distribution is proportional to this. Post, given x, is proportional. I could throw in those normalizing constants right there, but I'd still have to renormalize everything at the end of the day. And so it'll save you some time. So my posterior distribution looks like this. Keep it here. So this posterior, after some simplification, P given x post is going to be proportional to P to the sum of the xi's plus alpha minus 1, 1 minus P, n minus sum of the xi's plus beta minus 1. So I never soak up that minus 1. If I have real numbers in there, I always leave the minus 1 because I can recognize what distribution this is by isolating the minus 1. So as promised, this is a beta. And it has a couple parameters in here. How do I recognize them? They're these. So if I look at the beta distribution, there I get it. If I look at the beta density, this is a beta, and I should just say this thing right here is a beta with 2 parameters. Not to be confused with the beta function. They look entirely the same on the chalkboard. But that's the beta density, and that's what I'm going to use as my notation for it. So this is a beta, and this has these parameters. So this is going to be sum of the xi's plus alpha, and this one right here will be n minus sum of the xi's plus beta. And usually I call this like alpha tilde, beta tilde. So that's the notation I'll typically use. And so in a conjugate analysis, you get the same form as the prior for your posterior, but you change the arguments. And that's all that's happening in any conjugate analysis, is you're just updating the parameters in here. So we start with those. If you want to use the old adage of Bayes, the subjective sort of lingo, this is what I believe going in, whatever this shape is. And I've updated my beliefs with these 2 new arguments. That's how Peter Hoff says it in his book. So you're updating your beliefs sequentially. You see data, you change your beliefs. And sometimes people like to think about things that way. The way I've been saying it is it's like a likelihood analysis with a regularizer. But you can think about it this other way as well. I walked in with some beliefs. It's just a question mark of, is this really belief or is it an expression of ignorance? So what do you mean? So, and the only issue with that is humans, when they argue with each other. What do you mean you believe something walking in? That's the part I'm skeptical about. And so it raises a level of skepticism. And so I usually don't say this is my distribution of personal beliefs, but that's how Savage would say it to you. And I think it's okay if we're rational and reasonable, but people are not. So they just aren't. They're too emotional. Okay. So this is my posterior. We'll play around and we'll see this on several analyses, but you should be thinking about that anytime you see a parameter in a distribution. What's its conjugate prior? And you could do that today when you get home. Just pull out your book of distributions and see if you can recognize conjugate priors. I want to point out real quickly that P to the alpha minus 1, this prior that we're using, beta minus 1, I'll say proportional to that, this is the kernel, has a beta function that normalizes it. I was going to say something, I just forgot what it was. So let me just move on to the next thing and it'll come to me. So this beta density right here has an expectation. So let's think about that for a second. So expected value of P. Does anybody know what it is? One more time?
Alpha over alpha minus beta.
Okay, it's a good mistake to make. So if we did that, alpha minus beta, you should be thinking to yourself, I wonder if anything could go negative here. And so if alpha were smaller than beta, and there's no restriction on that, you would get a negative expectation. But the probability distribution was between 0 and 1. So that can't be right. So I always think about that anytime I write down an equation, where does this live? And if it's in the wrong part of the space, I know I've made a mistake. So it lives between 0 and 1. The correct answer, and several of you said it, is alpha over alpha plus beta. And I'll ask you what the variance is. Most people won't know what it is, but there's a closed form solution for the variance as well. And you might want to think about it in a future homework, but we're just going to lay off right now. But that lives between 0 and 1. So our posterior expectation I know what it is. I don't need the normalizing constant. I don't need to do a bunch of calculus with this. I could do some calculus if I wanted to figure all this out, but you would need to know a lot about gamma functions and how to do this integral. But it's just this. Alpha tilde over alpha tilde plus beta tilde. So that's sum of the xi's plus alpha over sum of the xi's plus alpha plus n minus sum of the xi's plus beta. And there's a little bit of cancellation in here. Those cancel. And so this whole thing is equal to sum of the xi's plus alpha over n plus alpha plus beta. I think that's important enough that I should write it bigger. So my expectation at the end of the day is this. It's almost like an average. So it's an average with a little bit of calibration to it. So it's an average that's been regularized. So there's some traction in all of this. So it's going to slowly move away from this, but it moves away pretty quickly as a function of n. And so if I had asked most of you what do you think p is, if I showed you 7 ones out of a sequence of 10 values, you'd probably say, I think it's around 0.7. And this might look something around 0.7 depending on what you pick for alpha and beta. If you pick alpha and beta to be extremely large, it would overwhelm everything else. It would overwhelm the data. But eventually the data would swamp out whatever value you picked here. So this is an increasing number, and that's an increasing number. So the prior has some impact on the analysis. We want to make sure that our prior isn't driving the whole analysis and the data speaks clearly. And so there's good reason to think alpha and beta shouldn't be big. Now remember what I was going to say. If I looked at this right here, this function, and I picked alpha and beta to be 1, so I'll pick 1 minus 1, 1 minus p, 1 minus 1, that's 1 right here. This is a constant function. So the beta, a beta 1, 1 is a uniform distribution. What I want to point out, if I would have said the conjugate prior was uniform, the posterior wouldn't be uniform. But uniforms do, or betas do, subsume the class of uniforms. So you could use a uniform, but it's not the uniform that's conjugate, it's a beta. So if you specify a conjugate analysis, you're not plugging in actual values for alpha and beta yet. You're describing that family of distributions, that infinite collection of distributions. So when I say a family of distributions, I mean you haven't plugged in numbers for the hyperparameters yet. So it's a whole collection of distributions. And that's what we mean by family. I do not mean something like the exponential family. That's a family over families. That's too big. Okay. I think next time we'll come in, we'll look at this analysis a little bit more, and then we're going to switch gears to a different distribution. See this all over again. And so I'll try to introduce little problems as we go through everything. One thing I want to show you before we get going, just what the sampling distribution looks like. So that's the binomial sampling distribution. So I need to plug in values to define this distribution, so it's not a family of distributions. So I plugged in n is equal to 10 and p was 0.7, and this thing, no surprise, peaks around 7. It takes on values between 0 and 10, and that's what its mass function looks like. If I saw data, and I plugged in the actual data into the likelihood function, I might see something like this. And this is a likelihood if I ended up seeing x was equal to 3, so 3 successes out of 10, this is what the likelihood function looks like. So the likelihood and the sampling distribution, while they look exactly the same on the chalkboard, you can't distinguish them until I tell you what's fixed. They are entirely different creatures. So, but the name of the game is take your sampling distribution, plug in your data, free up your variables, multiply it by a prior, bada bing, bada boom, you've got a posterior and you're now a Bayesian. So what you need to do next is defend all your choices. So, and tell us what sort of properties you're preserving. So we'll come back next time, look at this simulation, and then we'll switch over to the normal example. That's it for now, yes. Thank you.